Today, we're going to work with determining the simplest or empirical formula for a compound. And to do this, you either need to know the mass of each element that you have in your compound or the percent composition of each element in your compound. Then you can easily calculate or determine your simplest or empirical formula. So, our first example, we have 9.2 grams of an unknown. UNK is my abbreviation for unknown compound. It is composed of 2.8 grams of nitrogen and 6.4 grams of oxygen. Find your simplest or empirical formula. So, your first step with this particular problem is converting each one of your given grams of your elements over to moles. So it's a one-step stoichiometry problem. If we want grams to cancel, grams will go in the bottom for each one of the problems, and moles will go in the top. And since we're working with nitrogen in this first problem, we'll put a 1 mole here and also a 1 mole for oxygen because they're the same substance in the equality. Now notice that I'm only putting the mass of a single nitrogen and a single oxygen. I am not thinking of diatomics because we don't really know how many nitrogen atoms or oxygen atoms there are in this formula. So we want to forget that diatomics exist when we're working with empirical formulas. So we're going to round the mass of nitrogen to 14 from the periodic table and the mass of oxygen to 16. So we take 2.8 times 1, which is 2.8, divided by 14, and we get 0.2 moles of nitrogen. And 16.4 times 1 is 6.4. I think I said 16.4. So 6.4 times 1 is 6.4 divided by 16, and we get 0.4 moles of oxygen. Please notice that I'm labeling my moles of nitrogen and oxygen. So make sure you do that too, because that's going to help you in setting up your next step. In your next step, you're going to divide by your smallest number of moles. So that's why you need to know which one is which. So since nitrogen is our smallest number of moles, it will go on the bottom. So we'll do 0.4 divided by 0.2, and our answer is 2. So this means that when we write our formula for this compound, we will have 2 oxygen atoms. Then to figure out your number of nitrogen atoms, well, that's pretty easy because 0.2 divided by 0.2 is going to be 1. So we have 1 nitrogen atom. So this subscript for each element will be 2 oxygen for every 1 nitrogen. So your empirical or simplest formula will be NO2. When you write your formula, go on and write the elements and how they first appear or how they're wrote in your word problem. In our next example, we're given our percents. It says, what is the simplest formula of a compound with the following percent composition? We have 65.2% arsenic and 34.8% oxygen. Well, let's take a look at the last slide of notes here. And if you need to, go on and pause this video as you fill in your notes for this particular example. So this is our little saying to help you with your steps with percent composite or finding your empirical formula if you're given percent composition. So you do percent to mass, mass to mole, divide by small, multiply to whole. So it's kind of like a poem or a song. So with this example, since we're given our percent to mass is just simply changing your percent sign over to grams. So instead of 65.2% arsenic, it's 65.2 grams of arsenic. For oxygen, 34.8% oxygen, it's 34.8 grams of oxygen. Your second step was mass to mole. So that's that one step stoichiometry problem where we're going to convert each one of these masses over to moles using your periodic table. So if we want grams to cancel, you'll put grams in the bottom of each one of your problem and moles will go in the top. And it will be 1 mole of arsenic because arsenic is the element that's used in the equality, and 1 mole of oxygen, again, because we're working with oxygen and your equality. The 75 grams came from the periodic table, the mass, and rounding it. And oxygen, again, came from the periodic table, and we're forgetting that it's diatomic. We just want 1 oxygen because we don't know how many oxygen we have. So 65.2 times 1 is 65.2 divided by 75, and we get 0.8693 with some repeating threes, if I recall correctly. Do not round your number of moles. Try to leave at least 4 or 5 numbers if possible. When you go to calculate your mass to moles in your next one, 34.8 times 1 divided by 16 gives you 2.175 moles of oxygen. Again, don't round your number of moles in this step. Try to leave as many decimal places as possible. And this is why, because the next step is to divide by your smaller number of moles. So since arsenic is our smaller number of moles, we're going to divide that into our moles of oxygen. So 2.175 divided by 0.8693, and that gives us 2.50 and a whole bunch of numbers. We're just going to go on around that to 2.5. Okay. This is why you don't want to be rounding, because when you divide by small, this is going to get you to your closest whole number. If you got 1.99999, I would go on and say fairly confidently, it's okay to round up to 2. But when we get 2.5, we cannot round that up to 3. We have to stay at 2.5. Let's take a look at our number of number of arsenic will be 0.8693 divided by itself. So that means that whenever you look at your empirical formula, you have 1 arsenic and 2.5 oxygen. However, you know in a formula you can't have partial atoms. So this is where we're going to have to multiply to whole. And this is your final step that was mentioned on that page. So to ask yourself, what can I multiply 2.4 or 2.5 by to make it a whole number? Well, of course, 2. So we need to multiply both of these number of atoms by 2 to get them to whole numbers. So that means we'll end up with 5 oxygen atoms and 2 arsenic atoms. Or you could look at it like this, where you're going to distribute that 2 to the the formula that you started with arsenic as being 1 and oxygen as being 2.5, to get your simplest or empirical formula with all whole numbers. So you have arsenic is 2 and oxygen is 5. So again, I will give you this little saying, but if you're given percent, simply change your percent over to grams. If you already are given grams, then you just move on to this next step here, and you go mass to moles and divide by small. And sometimes you may be finished at this step that you don't have to multiply to whole. But like the second problem, we did have to multiply to whole. The first problem, we did not.